Welcome to QST Prep Academy. I'm your host, and today we've got a super focused explainer to get you field ready and completely prepped for that exam. We're breaking down EPA Method 1, sample and velocity traverses for stationary sources. Look, if you're going to be a stack tester, this is literally your foundation. You could have the most expensive, top-tier sampling gear on the planet, but if you don't pick the right measurement site or if you map your traverse points wrong, yeah, all that data is basically garbage. Method 1 is the big overarching guide that gives us the green light for everything else we do up in the stack. All right, here's our game plan for today. We're hitting 4 core pillars: site selection, traverse points, mapping, and cyclonic flow. Let's get right into it.
First up, Section 1, selecting the measurement site. So, the golden rule you absolutely need to know is the 8 and 2 rule. For an ideal measurement site, you've got to be at least 8 duct diameters downstream from any kind of flow disturbance. Think a bend, an expansion, maybe a visible flame, and 2 diameters upstream from the next disturbance. Now, we all know you might get stuck in a really tight industrial plant where you just can't hit those perfect numbers. If that happens, Method 1 gives you a bare minimum alternative. You have to be at least 2 diameters downstream and a half diameter upstream. If you're tighter than that, no way. You can't use this simplified procedure.
Check out this top diagram. When you're trying to find that perfect run, distance A is your upstream distance to the exhaust, and distance B is your downstream distance from the bend. By taking those actual physical distances and dividing them by your stack diameter, you can just map them right here on the bottom chart to find exactly what your minimum required points are.
Moving right along to Section 2, determining traverse points.
Now, the number of points totally depends on what you're actually testing for. If you're running a particulate traverse, meaning you're physically pulling solid particles out of that gas stream, the rules are strict. You've got to use figure 1-1. But if you're just running a straight-up velocity or volumetric flow rate test with zero particulate collection, the rules kind of relax a bit, and you switch over to figure 1-2. Let's say you hit the jackpot and actually meet that perfect 8 and 2 rule. Well, Method 1 rewards you. For massive stacks, anything over 24 inches in diameter, you only need a minimum of 12 traverse points. For smaller circular stacks, sitting between 12 and 24 inches, you just need 8. And if you've got a small rectangular stack in that same range, it's 9 points minimum. Hitting those 8 and 2 criteria is a huge win because it saves you a ton of sampling time out in the field. For those of you just doing non-particulate velocity testing, here's figure 1-2. You use this exactly like the first chart to figure out your minimum points based on duct diameters. But notice how the minimum point requirements drop off way faster here. It's just a much more forgiving curve when you don't have to stress about sucking physical dust perfectly straight into a nozzle. All right, guys, let's take a quick breather right here. If you're finding this explainer helpful, do me a huge favor and hit that subscribe button. And seriously, if you want to pass your QSTI exam and you're looking for that one-on-one help to get certified, shoot an email right now to qstiprepacademy@gmail.com. Write that down, send us a message, and we'll get you ready. Okay, let's climb back up the stack. All right, Section 3, mapping the cross-sectioned. So for circular stacks, your traverse points are placed on 2 perpendicular diameters. What you're doing here is dividing the cross-section into equal areas, meaning every single point represents the exact same amount of space. Notice how the points bunch up closer together near the edges? That's because the area of a circle expands as you move out, so those points have to shift to represent perfectly equal pie slices. Oh, and a quick pro tip. For particulate traverses, one of those diameters has to be in the plane containing the greatest expected concentration variation, which is usually matching the direction of whatever bend is right upstream. For rectangular stacks are honestly a bit easier to visualize. You just chop the cross-section into a grid made of equal, smaller rectangles. Then you drop your traverse point dead center, right at the centroid of each little area. It's basically just a perfectly balanced checkerboard. But what if your duct is a rectangle? How do you calculate the 8 and 2 rule then? Well, let's write this formula out. You use equivalent diameter, or DE. DE equals 2 times length times width, all divided by length plus width. Memorize this one. Whenever you're staring down a rectangular stack, write this out and run this formula first to get your equivalent diameter, then use that number to check your distances from any disturbances. And hey, before you start drilling any holes, you've got to remember the wall clearance rules. You literally cannot sample right up against the metal. The friction on those stack walls slows the air down and will totally wreck your data. If your stack is over 24 inches, stay at least 1 full inch away from the wall. If it's 24 inches or smaller, you still need a 1/2 inch of clearance.
If you calculate a point and it lands closer than that, you have to bump it inward to the adjusted minimum distance.
Finally, Section 4, checking for cyclonic flow. So, why does cyclonic flow even happen? Because industrial equipment is super aggressive. If your site is downstream of a cyclone, an inertial demister, a venturi scrubber, or a stack with a tangential inlet, that exhaust air is going to be spinning. And when the air spins, it's no longer flowing parallel to the stack walls. That means our standard pitot tubes simply can't measure the velocity accurately.
So how do we actually test for this spinning air? Out in the field, we use what's called the null technique. Step 1, level and zero your manometer. Step 2, stick your Type S pitot tube perfectly straight into the flow. That's your 0-degree reference. If your gauge reads exactly 0, awesome, the flow is totally straight. But if you get a pressure reading, move to step 3. You rotate that pitot tube, yawing it left or right up to 90 degrees until the gauge finally hits 0. You have to record that exact angle of rotation for every single traverse point.
And that brings us to the magic number for cyclonic flow, 20 degrees. Once you've got the rotation angle for every point in the stack, you calculate the overall average of the absolute values. If that average is greater than 20 degrees, no way. The flow condition is totally unacceptable. You literally pack up your bags because you cannot use standard method 1 there. Now, if you're forced to use the alternative measurement site selection procedure because your site is just incredibly cramped, the rules get even stricter. Let's write out one more big formula here. To prove an alternative site works, you don't just calculate the average angle. You have to use a highly sensitive 3D probe to measure both pitch and yaw at 40 or more points, and then calculate the standard deviation of those resultant angles using this formula right here. So here are your final acceptability criteria for those really tight alternative spots. Your average resultant angle still has to be less than or equal to 20 degrees. But on top of that, your standard deviation must be less than or equal to 10 degrees. Hitting these numbers proves that not only is the flow mostly straight, but it's also highly uniform without any crazy fluctuations going across the duct.
So after all that, are you ready for the field? We've mapped out our points and we've beaten cyclonic flow. Just burn that 20-degree limit into your brain. But it leaves us with a real question. What happens to your data if you perfectly map a site, but the plant's process changes completely right in the middle of your test? Think about that, and we'll tackle that exact challenge in the next explainer. Thanks for learning with QSTI Prep Academy.